Already discussed previously introduction of radioactivity. Now we have to discuss about loss of radioactive disintegration or loss of radioactive decay or radioactive displacement loss. Rutherford and Sadi discovered the laws of radioactive disintegration or radioactive displacement loss as follows. The first law: atoms of all radioactive elements spontaneously disintegrate and a new element formed. Alpha, beta, gamma radiations are emitted when radioactive substance disintegrates. That is the first law. Atoms of all radioactive elements undergo spontaneous disintegration. And the second law, radioactive disintegration is a random and spontaneous process. And third one is the number of atoms disintegrates in a radioactive substance per unit time, that is radioactive disintegration of a radioactive substance is directly proportional to number of atoms present in a given time. So that is dN by dt proportional to n. So this is called decay law. So these three laws are called radioactive displacement laws. Now we discuss about decay equation. Initially, or let n not be the number of atoms present in a radioactive substance at time t is equal to 0, and n capital N be the number of atoms left after time t. So after disintegration process, the remaining number of atoms capital N, that is capital N, present in the sample. So from decay equation, from decay law, so dN by dt proportional to capital N. So now removing the proportionality, dN by dt is equal to minus lambda n, where lambda is disintegration constant or decay constant. The negative sign indicates that n decreases as time increases. So that is the significance of negative sign. So dN by dt is equal to minus lambda n. Now shuffling these terms. So dN by capital N is equal to minus lambda into dt. So now integrate initial atom to final atoms when disintegration process takes place. And before disintegration process, after disintegration process. So that's dN by n is equal to minus lambda, so 0 initial time, final time dt. So then so it's integration, so log base e n naught to n limits. So here minus lambda, it's integration t. So limits 0 to t. So limits are substituting in this equation, you will get log base e n minus log base e n naught is equal to minus lambda t. So log this one, log a minus log b, so log a by b. So in that, log base e n by n naught is equal to minus lambda t. So no anti-lag, anti-lag on both sides we take. N by n naught is equal to e power minus lambda t. So there from this, n by n naught, n is equal to n naught e power minus lambda t. So this is called decay equation, decay law equation or decay equation. So the decay equation shows in the graph, that is the disintegration in radioactive substance exponentially decreases with the time. As the time increases, then radioactive substance disintegrates exponentially. So this is the conclusion from this graph. So now decay constant we define. So decay constant from decay law, dN by dt is equal to minus lambda n. So lambda is equal to minus dn by dt by n. Here the ratio of the rate of disintegration of radioactive substance per number of atoms present in the radioactive substance, that is called decay constant. So another way we define, so if small t, that is a time t is equal to 1 by lambda, put in decay equation, that is n is equal to n naught e to the power of minus lambda t. So this value substitute, so here, so n is equal to n naught e power minus lambda into 1 by lambda. So lambda lambda cancel, n naught e to the power of minus 1. So this can be write like this, that is equal to n naught by e. So n is equal to n naught by e value 2.718. So that simplifying you will get that is n is equal to n naught by e is equal to 0.37 n naught. So that is equal to n is equal to 37% of n naught. So from this the radioactive decay constant defined another way, the reciprocal of time for which the radioactive substance disintegrates falls 37% of its initial value. So that is known as a decay constant. Okay, thank you.